Precision Measurement for Machinists, a MasterTask multimedia program. Lesson 8, using optical and video comparators. There'll be 3 parts to this lesson. In Part 1, you'll learn the measurable features of a thread and how threads are specified in the inch and metric system. In Part 2, the methods of measuring threads are explained. In Part 3, you'll learn how the optical and video comparators are used.
Part 1. The parts of a thread and standard print notation. In order to accurately measure threads, you must know what the parts of a thread are called. This is the thread crest. The thread crest is the peak formed by a single thread. The thread root is the valley formed between 2 thread crests. Thread pitch is the distance between any point on a thread and the same point on the next thread. Pitch is normally measured between the crests of the threads. However, the terms pitch and pitch diameter can be confusing, since in the shop people tend to shorten the term pitch diameter and call it pitch. While pitch is measured from thread to thread, pitch diameter is measured in the other direction. You'll learn more about pitch diameter in a moment. The lead of a thread is the amount of linear movement that occurs during one complete rotation of 360 degrees of the mating part. The lead is normally not measured on a threaded workpiece. One important measure of a thread is the major diameter. It establishes the maximum material condition of an external thread. A thread any larger than this dimension would exceed the upper limit for the external thread. However, the MMC of an internal thread establishes the minimum size the thread can be. A thread any smaller than this dimension would be below the lower limit. How the major diameter is measured depends on whether it is an OD or ID thread. The major diameter of an OD threaded part is the diameter measured at the crests of the threads. The major diameter of an ID thread is the diameter of the thread measured at the root. One of the most important features to measure on a threaded feature is the pitch diameter, since it affects both the ability to assemble and the strength of the assembly. Pitch diameter is the diameter of a threaded feature measured between 2 lines which intersect where the widths of the thread and groove are equal. Special measuring instruments are used to measure pitch diameter, such as a pitch mic. The mic will have a specific anvil and spindle to match the thread to be measured. The minor diameter is another measured thread feature. It is measured at the roots of an OD threaded part. On ID threaded features, the minor diameter is measured at the crest of the thread. The cylinder created by the pitch diameter will have an axis. Geometric tolerances can be applied to that axis for both location and orientation. If the geometric tolerance is to be applied to either the major or minor diameter of a thread, it will be noted below the feature control frame. This is the standard form for thread notation found on prints in the inch system of measure. The common standard is the unified inch screw threads, indicated by the abbreviation UN in the thread specification. When the letters UNF appear, the F means it is a fine thread. The UNC designation identifies a unified coarse thread standard. Coarse threads will have fewer threads per inch than fine threads. For example, a half-inch diameter fine thread has 20 threads per inch, where a half-inch coarse has 13 threads per inch. There are other UN series designations, such as UNEF for extra fine, or UNJC, which specifies a radius for the root of the thread. Other thread designations exist, such as NPT for National Pipe Thread and ACME for ACME threads. If you are unsure of the thread specification called for on a print, contact your supervisor before making a measurement. The values found in the unified thread notation on a print should not be considered the actual dimensions of the threaded feature. For example, if a 1/4-20 screw is going to mate with a 1/4-20 tapped hole, there must be a certain amount of clearance between each of them. The screw and the hole cannot both be 1/4 inch in diameter, or the parts would not have enough clearance to allow them to thread together. Therefore, the values found in a thread notation only provide a general guide to the size of the threads required. On some prints, you will find the measurable tolerance limits for a threaded feature listed along with the thread notation. If those tolerances are not provided on the print, you will need to find the measurable tolerance limits in a reference manual, such as Machinery's Handbook. The first number in this inch thread specification, therefore, represents the size notation of the major diameter of the thread, not the actual nominal size of the major diameter. The actual nominal and tolerance limits of the thread for this size notation must be found before measurement can occur. If the major diameter of the feature is less than 1/4 of an inch, the diameter will be expressed as a whole number from 0 to 12. For example, a number 10 screw will have a major diameter of 190 thousandths of an inch. You will need to refer to a chart of standard dimensions to find the tolerances of the pitch diameter for the thread specified on the print. For example, this chart lists 1/4 28 limits for unified fine thread as having a maximum pitch diameter of 226 thousandths and 8/10 and a minimum of 224 thousandths and 3/10. The second number in the unified thread notation system is the threads per inch, also abbreviated as TPI. The TPI equals the number of crests that would occur within 1 inch of the threaded part length. This example calls for 20 threads per inch. Remember, pitch is the distance between one thread and another, and is not the number of threads per inch. Notice that the pitch value is not included in the standard notation for inch threads, and is therefore not a value that will be directly measured on a threaded feature. However, the pitch of a thread directly affects the TPI of a thread. For example, as the pitch gets larger, the TPI gets smaller. Therefore, the pitch is indirectly measured by measuring the TPI. Since the TPI is the number of threads in 1 inch, we can simply divide 1 for 1 inch by the TPI number to find the distance of one thread, in other words, the pitch. For example, on this 1/4 20 screw, divide 20 into 1 inch. The pitch of a properly formed 1/4 20 screw thread is therefore 50 thousandths. The next number and letter in the unified thread notation indicates the class of fit. It's very important since the class of fit determines the actual tolerance limits of the thread features. The numbers range from 1 to 5. They indicate the relative fit, with 1 being the loosest and 5 being the tightest. The number 2 is the most common class of fit. The size limits of a thread gauge, such as a ring or plug gauge, will be established by the specified class of fit. Be sure the gauge you are using matches the class of fit required by the print specifications for the feature being measured. The letter that follows the number indicates whether the thread is an ID or OD thread. Capital A simply means that the threads are to be formed on the outside of the workpieces. Capital B indicates ID threads. If these threads were to be left-hand threads, there would be a capital LH following the class of fit. If there are no LH letters, they would be right-hand threads. Like the inch notation, metric threads have a standardized notation. These standard codes will be shown on the shop print next to the feature. All metric threads begin with a capital M for metric. The next number is the notation for the major diameter in millimeters. As with inch threads, this does not represent the actual diameter. Refer to a reference manual to find the actual tolerance limits of the major diameter. While pitch does not appear in inch thread notations, in metric notations, the second number is the pitch in millimeters. Since pitch is not easily measured with shop instruments, refer to a reference manual to learn the pitch diameter and the tolerances that apply. For metric coarse threads, no notation is made for the pitch. That is because the pitch is standardized based on the major diameter notation of the threaded feature. A reference chart will indicate the standard sizes. For example, the pitch of metric coarse threads, whose major diameter notation is 8 millimeters in diameter, will always be 1 25/100 millimeters. When a fine thread has been designated, the pitch will be noted on the print after a time sign. For this fine metric thread with X 1.0, the pitch is 1 millimeter. This value is the true pitch, and not the pitch diameter or the threads per millimeter. Behind this dashed line are a series of numbers and letters that are standard symbols for thread form tolerances. These are similar to the numbers used to describe the class of fit in the inch system. There will be both a number and a letter. The numbers are called the tolerance grade. The tolerance grade numbers can range from 4 to 8. 4 provides the tightest fit, 6 a medium or average fit, and 8's a loose fit with the mating part. The letters G and H represent the tolerance allowance. The G allows some allowance, while H has no additional allowance. A lowercase g or h means it is an internal metric thread. Uppercase means it is an external metric thread. Some metric threads will include a second set of tolerance notations. The first set always applies to the pitch diameter. The second applies to the major diameter of OD threads and to the minor diameter of ID threads. If the metric thread notation includes a pitch diameter, it will appear within the normal notation and typically include the letters PD for pitch diameter. Because the same threaded feature can be specified in either the metric or inch system, you may find metric prints with inch thread notations. Look carefully at thread notations to be sure you understand the measuring system being used. Part 2. Methods of measuring threads. In order to produce threaded parts of acceptable quality, you must understand the thread specifications, select the correct gauge, and be able to measure threaded features accurately with the gauge. In some cases, where a variable gauge is used, such as a micrometer, you must be able to compare the values on the gauge to the thread specifications. To understand the thread specifications, you must be able to correctly read the notation on the print and look up thread limits in a reference guide. As with all features, the tolerances of these dimensions will determine the measuring instrument to be used. Since threaded features, by their nature, must assemble with some other component, the use of go, no-go gauges is perfectly acceptable, since they are checking the ability to assemble. Before checking threads for accuracy, allow them to cool. Clean all dirt, oil, and chips from the threads and your measuring instruments. The major diameter is part of the thread specification in both metric and inch measurements. On OD threads, the major diameter can be measured with an OD mic. Snap gauges may be used for checking both the pitch diameter and the major diameter of OD threads. This gauge has 2 preset gauge points. The top gauge is the go gauge, which is set to the upper limit of the pitch diameter. If the workpiece passes this gauge, the pitch diameter is not oversize. The lower gauge is a set of rolls set to the lower limit of the pitch diameter. If the piece passes these no-go rolls, the pitch diameter is undersize. This gauge checks the maximum pitch diameter on the go gauge and the minimum major diameter on the no-go gauge. Measure the overall length of the threaded hole or OD with a scale or caliper to be sure that it is in tolerance. Go, no-go plug gauges are typically used on threaded holes. The go gauge is on the green end, while the no-go gauge is on the red end. For threaded holes, a go thread gauge will check for the maximum material condition of the pitch diameter. As a tap wears, this go gauge will detect the problem first. A no-go thread gauge will be used in addition to check the least material condition pitch diameter. Go, no-go ring gauges may be used on OD threads. Each gauge is marked with its specific thread size. These gauges simultaneously check many attributes of the thread form, such as angle, taper, roundness, and lead. Thread the gauge over the entire length of the thread. This gauge begins to bind as the gauge moves toward the shoulder, indicating this thread does not meet tolerances. When the go gauge binds on the threads, the pitch diameter could be above the upper limit. If a go gauge threads properly, as with this plug gauge, remove the go gauge. Now screw the no-go gauge onto the part. When the gauge starts to bind, stop. Do not force the gauge. Then count the number of revolutions as you unscrew the no-go gauge. If the workpiece is measured in inches, and it takes more than 3 full turns to unscrew the no-go gauge, the pitch diameter is larger than the allowed tolerance. If the workpiece uses metric dimensions, you are allowed up to 2 full turns to unscrew the no-go gauge. Because most plug and ring gauges are designed to check the pitch diameter, one feature dimension is not checked at its tolerance limits. On go plug gauges, the minor diameter is not tested, and on go ring gauges, the major diameter is not tested. Since go, no-go gauges do not provide a measured value of any feature checked, you may be required to measure pitch diameter on OD threads with a gauge which reads variables. To do this, you can use a pitch micrometer. Check the markings on the pitch mic to be sure it can read the thread size. Some pitch mics have replaceable spindles and anvils to match the thread pitch being measured. Install the correctly matched set. The pitch micrometer is read just like other micrometers. A tri-roll pitch gauge can also be used to measure the pitch diameter of OD threaded workpieces. The tri-roll pitch gauge has 3 threaded rollers which engage the threads on the workpiece. The rolls mounted in the gauge are selected based on the thread pitch and diameter being measured. Multi-threaded rolls measure the cumulative effect of thread variations across a number of threads they engage. In effect, they measure the functional size or maximum material condition of the pitch diameter. A dial indicator gives a reading of the measurement. The indicator on most tri-rolls is accurate to 1/10,000th of an inch. One rotation on this indicator occurs with each 10,000ths of an inch. Therefore, it is important to note the number of needle rotations when measuring to be sure errors of more than 10,000ths can be caught. A mastering gauge may be provided with the tri-roll to set the dial indicator to the correct value. Note the pitch diameter of the master. In this example, the size is 226 thousandths and 8/10ths. By checking the specification for the quarter 28 thread, this value is the upper limit of the pitch diameter. By placing this master in the tri-roll, the upper limit can be set to 0. The dial clamp is loosened and the dial is rotated to place the needle at 0. According to the thread specifications, the lower limit is 224 thousandths and 3/10ths. The difference between these is 2 thousandths and 5/10ths. Therefore, a distance of 2.5 thousandths is marked on the dial as the lower limit for this thread measurement. Press down on the opening lever and place the master between the rolls again. As you release the lever, note the number of times the needle rotates. In this example, 2 rotations. Now measure a workpiece. Slowly lower the lever as you count the rotations of the needle. Be sure the same number of rotations occur. Then look at the indicator. The needle must be inside the marked tolerance zone. Repeat the measurement along the whole length of the thread to check for taper. After checking threads for dimensional accuracy, visually inspect them. Look closely at the thread crests. Threads with correctly formed crests are called full threads. Threads with flat crests like these are called unfilled threads. Unfilled threads are usually not acceptable. Make sure the thread meets both dimensional as well as finish requirements.
Part 3. Optical and Video Comparators.
An optical comparator may be used to check OD thread features as well as other workpiece features. The workpiece is mounted to a stage. The comparator, also called a shadow graph, shines a light on the workpiece and projects a magnified shadow onto a screen above. It is from this shadow that all measurements and comparisons of workpiece features can be made. The amount of magnification can be controlled. This comparator has 10 times, 20 times, and 50 times magnification settings. Because the image is magnified, the optical comparator is especially useful when measuring small workpiece features such as threads or grooves. A standard chart is etched into the glass screen of this comparator. The chart has precisely marked lines and curves for use in comparison and measurement of workpiece features. The chart can be rotated using the rotation knobs to measure angles and other features. This digital comparator displays the position of the table in each axis as well as the rotational angle of the chart on the screen. The stage can be positioned using the x-axis, which moves the stage horizontally, and the y-axis, which moves the stage vertically. This comparator has motorized axis feet adjustments as well as manual adjustment knobs. The workpiece can also be rotated between the centers on the stage when viewing a feature such as threads. The table, to which the stage is mounted, can be rotated around the y-axis. The table is rotated when measuring threads so that the angle of the table matches the helix angle of the thread. This allows the profile of the full thread form to be viewed on the screen. Since many measurements are made by moving the table and reading the digital displays, the power of magnification will affect the scale of the lines on the standard chart. This key indicates the scale of the smallest division on the chart at each level of magnification for this comparator. For example, at 50 times magnification, this smallest grid division represents 1/1000th. At 20 times, that same distance represents 2.5 thousandths, and at 10 times, the smallest division is 5/1000ths. The grid itself has several divisions. At a 50 times magnification, the box created by the large black line is 10,000 square in size. The next smaller box is 5,000 square, and the smallest box is 1,000 square. Since the interior of the thread form will be viewed in this example, it is important to thoroughly clean the workpiece of all coolant and chips. Coolant collected in the bottom of the thread form will cause an incorrect root radius measurement. Since many of the specific tolerances of threaded features are not specified on prints, locate the root radius and other thread dimensions for the thread size in a reference guide. For this quarter 28 UNF thread, the helix angle is 2 degrees, 52 minutes. A degree is 1/360th of a complete circle. Each degree is further divided into 60 equal parts, each of which is called a minute. Each minute is divided by 60 again to establish a second. This is the symbol for degrees, while this is the symbol for minutes, and seconds are denoted with this symbol. Once the helix or pitch angle has been found in the reference guide, loosen the clamp and adjust the table to the specified angle. Notice that each degree on the scale is divided into 2 spaces. Since there are 60 minutes in each degree, each space represents 30 minutes. The 0 line on the vernier scale points to the number of whole degrees. Here, the 0 line is located past the 2 degree and 30 minute space. Therefore, the degree scale reads 2 degrees, 30 minutes. The vernier scale is divided into 5-minute segments. The matching line would be between the 20 and 25-minute lines. Therefore, the number of additional minutes is 20. Add the 2 values to see that the table is just past 2 degrees, 50 minutes. Mount the workpiece to the stage and position the threaded portion in the light beam. Focus the light to create a sharp image on the screen using the focus knob. One accurate way to measure the root radius is called the angle method. First, align the bottom of the root with the baseline of the chart. Since this is a 60-degree thread, one side of the thread form is aligned with the 60-degree line on one side of the chart. Then the x-axis register is zeroed by pressing the X0 set button. Now the workpiece is moved on the x-axis until the opposite wall of the thread aligns with the opposite 60-degree line. Reading the x-axis register now reveals the radius of the root. In this example, the root radius for this thread is almost 6 thousandths. It is also possible to measure the thread length using the comparator. Position the end of the part so that the vertical line on the chart overlays the end. Zero the digital display for the x-axis. Using the x-axis handle or power feed controls, move the threaded section to the last full thread. To check that the thread is full, rotate the workpiece and watch the thread form to locate the last full thread. Place the center line of the chart in the center of the radius. The x-axis display will indicate the length of the threaded portion. Check this value against the print. The angle of a feature can also be checked, such as this groove. The angle of this groove should be 40 degrees. Mount the workpiece on the stage, then move the table in X until one wall of the groove coincides with one of the lines on the chart. The chart indicates this feature does match the 40-degree specification. The other side of the groove is also checked. The radius of the groove can also be checked on the chart. Rotate the chart to 180 degrees to place the arcs on the bottom of the chart. Check the digital display to be sure that the chart is at 180 degrees. Place the shadow of the arc over the line which most closely matches the arc on the chart. Since the magnification is at 50 times, each line equals 1/1000th. Therefore, the radius of this arc is 8/1000.
Newer comparators, called vision systems, use a video camera and are connected to a computer to control the adjustments of the unit. A light source below the glass plate shines up to the camera in the head above, which sees the feature on the workpiece to be measured. A group of LEDs surround the lens of the camera above the plate. The number of LEDs will vary depending upon the model of the vision system. On the computer screen, you will see an area where you can control which set of LEDs are currently lit. The image of the camera is displayed in the lower right corner of the screen on this brand of system. A slide is used for practice and when setting up the vision system. 3 axis knobs are used to position the feature in the view of the camera. The x-axis knob moves the table left and right. The y-axis knob moves the table back and forward. The z-axis knob is used to raise and lower the camera to focus the image of the feature being measured. During focusing, 2 vertical green lines appear on the screen. When the green lines overlap, the lines will appear as one and the object will be in focus. In the upper right corner of the computer screen is the digital readout, or DRO. As the axis knobs are moved, the DRO shows the current relative position of each axis. Once the start point of a measurement is in the camera window, the DRO can be zeroed by pressing the space bar on the computer. Your part print will indicate whether the features to be measured are in inch or metric and any other specifications for the part. Directly below the DRO window are buttons to toggle between selections of Cartesian or polar coordinates, inch or metric values, degrees or decimal values for measuring angles, and centigrade or Fahrenheit temperature values. Below the DRO is the light control. The slider controls the light level. The 4 buttons shown here control the surface light. They can be controlled as one entire unit, by rings, octans or quadrants, or by individual sectors. Depending on the system, the surface light may have 1, 2, or 5 rings and 4, 16, or 40 programmable sectors. As measurements are made, each feature is displayed in the schematic window. The icons below the schematic window indicate the type of view selected for the window: isometric, front, right side, or top. The rightmost button selects the part coordinate system. Below the schematic window is the program interface window. 3 sets of icons are located here. The feature icons let you select the type of feature you are about to measure. They include points, holes, arcs, angles, and surfaces. Once the feature type is selected, the construction icons can be used to create a feature you intend to measure. In this example, a circular hole is to be measured. Begin by selecting the circle from the feature icons. Note that when the mouse rolls over the icon, the name appears. The Vision Tool icons are used to make measurements of the feature currently displayed in the camera window. With the circle selected, select the Feature Scan Circle Vision Tool icon. Moving the mouse over the camera image displays a crosshair that indicates where a marker will appear once the mouse is clicked. Clicking on 3 points on the ID will enable the computer to calculate the diameter of the hole. Comparing the location of the purple ring will enable the operator to make sure the measured diameter coincides with the image of the hole. The ID dimension just checked will appear in the summary window above. It indicates it is a circle and the diameter value. After a second circle is measured in the same manner, the schematic window shows the location of both holes relative to one another and their diameters. To get a calculation of the distance between the centers of both holes, the distance icon is selected. The operator then clicks on Circle 1, then on Circle 2. A pop-up window appears that's titled Choose Correct Solution. 3-dimension lines are available, one for the outside edges of the circles, one for the distance between the inside edges of the circles, and the one highlighted in purple, which is the distance between the two centers. With this line selected, the operator clicks OK. Now the line between the centers appears on the schematic window. The distance measurement now appears in the results summary window as distance 3. Angles can also be measured by clicking on the angle icon. 2 points are selected along the length of the line by clicking the mouse at 2 locations. Notice that despite the operator moving the image, the line just drawn stays in position on the workpiece. A second line is then drawn by clicking at 2 locations along the other edge of the part. The solution window shows 4 lines with arrowheads that identify different angles that might be measured between these 2 surfaces. It automatically selects one of them and highlights the line. In this case, the print requires measurement of the outside angle, so the operator clicks on the correct line. Once the operator clicks OK, the summary window shows the angle is 45 degrees. Radiuses can also be measured. The arc icon is selected. Within the Vision tools, the 3-point Scan Arc tool is selected next. 3 points along the arc are then selected with the mouse. The resulting arc appears and the radius value is displayed in the summary window. If a feature is not easily aligned by the operator with the normal tools, the best edge icon in the Vision tools can be selected. The 3 points are now selected along the arc. The software then finds the edge of the arc and indicates the alignment with this small circle. The outside of the circle can be clicked on and dragged out to increase the length of the arc on the display to make it easier to see. As before, the value of the radius is displayed in the summary box above. Each feature is listed in the feature box in the order in which it was measured. In this example, the last arc was the 6th measurement. Your video measuring system may have different features in software. Refer to the manual provided with your equipment.
This completes your lesson on thread measurement and optical comparators. Contact your instructor to learn your next step in this course.